I imagine most of you are probably on Twitter, so feel free to take photos and post it on Twitter. Use hashtag FOSDEM, FOSDEM. Let's get trending on Twitter. Because there's no actual official registration, FOSDEM doesn't really have a good exposure like in lanyard and websites like that. We should make it like a trend. Okay, so this talk is about continuous integration at a distribution level. And here we are with Martin Pitt. Martin Pitt works with Ubuntu, I guess. He works on Linux plumbing upstream and in Debian, Ubuntu, systemd and stuff like that. And have created and maintained the distro level CI in Ubuntu. Please welcome Martin for the talk.
So welcome everyone. Yeah, it's a pleasure to speak in front of so many people. I'm overwhelmed. And of course, lots of thanks to the FOSDEM organizers and the volunteers. It's a great conference, so thanks a lot. So yeah, I've been an Ubuntu developer since pretty much its inception in 2004, and a Debian developer even longer, a long time. And in Ubuntu, we have practiced continuous integration at the distribution level. That is, we do test-based gating for like the 30,000 packages that we ship. And as far as I know, we are still today the only major distro which does it with that rigor, like test-based gating of the development of the distribution. And so I want to share some thoughts and experiences and maybe convince you that it's a good idea. So what I'm going to do. So first, why did we do this? And then how do our tests look like these days? How do we use them for gating? And then I want to lose a couple of words about the infrastructure where we run all this, because at this scale, you imagine it's not exactly easy. And then how did it change our life doing all this? And then we should have about 10 minutes of Q&A. So where did we come from? In the first few years of Ubuntu, we had this 6-month development cycle, and in the first 4 months, this was basically the anything goes, toss everything over the fence, feature development. And then we hit feature freeze, and in the remaining 1.5 to 2 months, we tried to fix about half of the regressions that we introduced in the first 4. And during that time, as a developer running the development release, it became kind of a daily morning exercise to fix your broken boot, or fix your broken Xorg, or try to restore half of the packages that your upgrade removed underneath you because you weren't paying attention. So while you learned a lot about how all the system worked, it was certainly not a very enjoyable experience for non-developers. And as a result, we did not have a lot of non-developers using the development release. And as a result of that, we were losing a lot of potential feedback for how the development series worked in real-life scenarios. We didn't get non-critical bug reports, and as a result, a lot of regressions crept into the stable releases. And another problem was that in the distribution, you were facing a lot of archive-wide changes. Things like library transitions, or introducing a new Qt or major Python version. So back then, these things were often not finished. People basically tossed them over the fence, half done, saying, oh my God, I have this deadline to make, or there's feature freeze next week, so let's dump it all in and sort it out later. And in the end, it became someone else's problem. And usually in the end, the release team had to clean up all these bits and kick out packages and desperately rebuilding packages against the API, and it was just a horrible mess. So once Ubuntu became popular enough and was being used in mission-critical deployments and commercial projects, this was simply not good enough anymore. So we set down like a strict goal. The development series must be stable and usable and safe to be used at all times. Nobody's able to knowfully break it anymore. And so by using this kind of continuous testing, continuous integration, we basically want to ratchet towards perfection. We never ever wanted to have a bug which we can automatically detect land in the development release. And yet another problem was that many upstreams already have test suites. It's just that like every project does them differently, so there is no uniform and thus automatic way to actually run them in the distribution at the time when you need it. So that was the situation. So initially, like everyone else, we started with some rather naive approaches. So we set up a QA team, and that created several iterations of standalone test suites, like Ubuntu desktop tests, Ubuntu server tests, and whatnot. Tossed them into Jenkins and run it every day, and then basically pestering people about, you broke the tests, and please fix it. Well, of course, none of that really worked, because it's too late. I mean, at that point when they detected it, the damage was already done. Also, it's this never-ending blame game, like developers pointing to QA, but it's your tests that are broken, and QA pointing to developers, no, it's the software that broke. Also, none of that was really reproducible and easy to replicate for a developer. So the conclusion from that was, the only people who are able to be responsible for the test in a meaningful way are the developers of the very software. So developers are responsible for testing, they're responsible for gating, and the QA team basically only does the infrastructure and making sure that the test results actually arrive, and provide some kind of consulting to people. Like if someone has a question, how do I simulate, I don't know, a Wi-Fi card or Excel or whatnot, then the QA team could help you with that. But it must be possible for every developer to reproduce tests easily without reading lots of manual pages. So the idea was, instead of having these centralized tests, we would put the actual test for a source package in the source package itself, where developers can develop them by themselves and they don't need to go through any QA process. And these tests would then be triggered when either the software itself or any of its dependencies would get updated. And we, of course, would use these tests for actually gating, so once these tests break, so your package doesn't land, period. And this was named auto package test. This is both the name of this whole kind of test, and it's also the name of the tool that you actually run to execute the test. And back then it was submitted as a Debian enhancement proposal number 8, which is why you can still hear a lot of people calling them Deb 8 tests, so don't be confused. How do these look like? So this is one of the simplest and oldest tests that we still have in the archive. So it's the kind of toy example where you begin. So every source package with test needs to have a Debian test control, which gives the test metadata. Basically, it enumerates all the tests that we have, and it says, in order to run the simple gzip test, we need to have these and these packages installed. And you can also give other properties, but I'm going to this later, and this one doesn't need anything. And so for every test that you enumerate there, simple gzip, you need to have an accompanying Debian test/test name. And if you see here, this can be very simple. It's basically a smoke test that gzip and gunzip does what we expect it to do. And so the contract is, if the test that you run exits with 0, then it's passed, and otherwise it's failed. So you can write the test in any language, you can compile it if you wish, and so that keeps it pretty flexible as a developer. So once you have the test, how do you run them? So this is the auto package test program. This is the thing responsible for creating a temporary test bed, copy the test inside that, run it, make sure that all the logging is right, you get the results back and any kind of artifacts back. And you can influence the final behavior of the test. The details aren't that important. And it supports various backends there, which you can run the test in. So one of the oldest ones that we have is like a Chroot, which you see in the second row here. Chroot is basically Debian's tool to manage, build and manage a couple of chroots. So very simple. But of course, this kind of limits the things you can do. So you can't start services, you can't interact with the kernel, because that doesn't work in chroots. So after we created auto package test, these new fancy technologies came along, QEMU, containers, whatnot. So these days, we have backends for LXC, LXD, QEMU, arbitrary SSH hosts, or cloud instances, and ADB, if you want to run something on Android. And these days in production, we're actually using QEMU by way of using OpenStack instances. So you have a full virtual machine to mess around with. And we use that for x86s and the Power 8. And for the other two architectures, ARM and S390, which we support, we run them in LXC because we don't have OpenStack integration yet. So a slightly more useful example is a schema that we use in a lot of libraries. So we basically do a simple compile, link, run cycle to make sure that the library that we ship or update still works. So this is a simple test metadata. Should be straightforward, I hope. And this is what the test does. Basically, it creates a simple C file, which, like in this case, it interfaces with systemd's login. So we instantiate the login monitor, call it, and basically make sure that the smoke test is right. Then we call GCC on it and run the program, and like if it succeeds, the test is good. So at first sight, this looks very simple, but on second look, there's actually lots of things which can go wrong. So for example, we update the program to a new upstream version, and our development package is missing to specify a new dependency. So it's trying to use a header file, which is just not there. Or it actually forgets to install new header files. Or like the package config file is wrong, and we did have new upstream versions which ship with a broken package config. Like all of that happens. So as I said, you'll see the same pattern in lots of libraries in Debian and Ubuntu these days, so it is useful. And a more like intricate example is, for example, the one from our systemd package where we run an upstream test. So upstream ships a test /networkd test.py, which exercises networkd. And as I said, normally the test needs to live in Debian /test, but with the test directory clause, we can say that the test is to be looked at in a different directory. So in this case, test/networkd test.py. And this is a way how we can interface and run upstream tests by basically just giving the metadata for the test, and that's it. And you also see the new restrictions column here. So this is where you can say like how well isolated does my testbed needs to be. So in this case, we need to have root, and we also need to run it at least in a container, because networkd you need to set up a couple of VEs and start services, and for example, this wouldn't be safe to run into root. And there is one, a stronger version of that would be isolation machine, which we, for example, use in the network manager test. That loads a kernel module like Mac 802.11HWSIM, which simulates Wi-Fi devices, and this is the kind of stuff that doesn't work in the container. Also, our kernel tests, they do really nasty things to the testbed and beat them to a pulp, and so you really want to nicely contain this in the VM. It's just not safe in a container. But I don't actually want to go too much into the details of that. I just want to give a broad overview of what's possible there. For example, in systemd, we have tests which simulates a suspend for seeing how login works, or closing and opening of the lid. Or we create with SCSI debug, we create a loops partition and make sure that systemd integrates this properly. Or we install a couple of, let's say, mission critical packages like dbus, network manager, or XOR and LightDM, and make sure that with every new systemd upgrade, everything starts and there are no failed services, and that you can reboot the testbed 20 times without failures. So that said, when we started this in like 2012 or so, we still had a very few tests, as you see, and then we started to introduce this into Debian. And since 2014, I'm quite happy that Debian also runs these tests, except that it doesn't use them for gating it. And you see the adoption curve is really nice. These days we have more than 6,000 packages which have auto package tests. And considering that you also cover their dependencies implicitly, there's quite a nice coverage already. I mean, it's still far away from the 30,000, but it points into the right direction. By the way, the big leap that you see here was kind of sort of cheating. So we figured out how a generic way to test Perl and Ruby and DKMS modules, because they all look very similar, so we have a central way to run them. And so that explains the nice jump. So now that we have the tests, how do we use them for gating? Initially, there's a developer who prepares a new package update, say GDK. and uploads it to the distribution. That happens with dput. That's just the standard Debian tool to upload a package. But this does not land directly into the Ubuntu development series, but instead it goes into something which we call the proposed pocket. And this is a kind of an overlay on top of the development series, where all the new stuff is being uploaded. And it acts as a staging area for basically CI. And this one has no human users, because by definition, that's the bit that is broken. And then we have a thing called proposed migration set of scripts. If you are from a Debian background, you might also know it as Britney. And this then does all the necessary checks on it. So it tests that the new GTK builds on all the architectures where we expect it to, that it is installable everywhere, that it doesn't break installability of other packages. So we do this for all the 30,000 packages, and that ensures that library transitions can only be complete and you don't knowingly introduce uninstallability. And for the purpose of this talk, it also triggers tests, both of GTK itself and everything that uses GTK, like all the reverse dependencies. And only once all of that is good, proposed migration then lands either GTK itself or the group of packages that are kind of belong together into the development series. And with all of that, we ensure that packages in devel, they never regress on architecture support, they're always installable, and in theory at least, the tests never regress. Well, that's the theory part, but for the most part it works. And so of course, in this case, if GTK breaks something, the developer then might need to do further uploads to adjust GTK users to like new API or whatnot. So, and this is a page which we automatically generate where developers can check the status of their packages. So in this example with GTK, we for example see here that like it didn't build on PowerPC 64 yet, and on IF86 it has an uninstallable binary package, and that like one reverse dependency Unity just failed the test. So this is a very simplified output. So normally we test on 5 different architectures and not just one. And also we wouldn't actually start the test before we know that the package builds and is installable, because otherwise it's pointless, but like it should illustrate the point. And this is actually still a very simple case. Consider updates of glibc, Python, Perl, or apt, and they literally trigger thousands of tests. Like every time we upload glibc, we trigger 5,000 tests times 5 architectures. So our machinery takes like about 2 days to grind to that. But the nice thing is, after these 2 days, you can actually land this stuff with confidence, instead of just saying, yeah, I hope that it breaks nothing, because it always does. And of course, the exact same thing applies to updates of stable releases as well. So it's the exact same thing. People upload to, say, Xenial proposed. Xenial is our current LTS. And then it goes to all this machinery, and only if it's green, we can actually publish it. So that's the structure of the test. I want to explain a little bit the infrastructure and where we run this, both because I haven't really seen this kind of structure anywhere else, and also, to be completely honest, I'm a little bit proud of it. So, like many other people, we of course started with Jenkins. And that was okay when we had like 20 tests in the beginning, but already then it was quite brittle. When every update of Jenkins, then you read through 3 screenfuls of Java exceptions, and it's pretty hard to maintain, and it's really not easy to replicate locally if you want to develop the infrastructure. And we got a lot of losing test requests, and it's a single point of failure. And at a scale of 30,000 packages, it just doesn't work. So we needed something better. So I sat down the other day and designed something on a microservice architecture, which should use standard cloud technology as far as possible. And I wanted to have small and loosely connected components. So where it starts is what you could call a policy entity. So this is a thing which wants to trigger tests, and then wait for the result, and then making decisions based on these test results. This can be proposed migration that I was just explaining for the distro, but it could also be GitHub, for example, where you want to use it for gating pull requests. And there's a couple of other consumers about that, for that. And the only thing that this policy entity does is it puts test requests into an AMQP queue. So we use Rabbit for that, which is basically standard implementation. For those who don't know NTP, like very simply, it is a job distribution system. So you have a couple of queues where you can put in requests, and then consumers can take out the requests. And NTP ensures that all of this is very robust. It is atomic. You can arbitrarily parallelize it, and it is a very simple API. So basically, a consumer of that, if you want to read test requests and do your thing and then acknowledge the result, and it's basically 5 lines of Python, or you can do it in a single line of shell. And like NTP system ensures atomicity, or if anything breaks and the request doesn't get fully processed, it gets punted back to the queue, and the next consumer basically reattempts it. So what it does in our case, we have a bunch of workers up there, and they basically take requests from the queues that they can service. So we have workers for x86, for example, and then separate set of workers for PowerPC, because these tests run on a different cloud. So you configure the workers a little differently depending on like what kind of service they can support. So they take the request, build an auto package test command line, run the test in the cloud, copy back the results, and store them in a permanent thing, which is Swift in this case, and then at the end acknowledge the request. And if anything goes wrong in the middle, it goes back to the queue and you never lose a test request. And like at the moment we have many dozen of these parallel workers, so that it can scale with the size of the infrastructure, and it's quite painless to set up. And for those who don't know Swift, this is basically OpenStack's standard, like OpenStack developers forgive the simplification, but it's basically a distributed network file system. It has a simple REST API for querying and uploading, and downloading is basically you give someone an URL and you can watch it in your web browser or download it with a curl or URL lib or anything. So it's pretty simple to use because it's a standard component of the cloud. I, as a consumer of the cloud, don't need to worry about it, and it's separate from all the instances you set up. So it's basically the data is safe there. And finally, once the logs and our artifacts are in Swift, then the original requester can poll for the results and wait for the test results to arrive and then do its decision, and the loop is closed. And finally, there's also a web UI, this results browser, which developers can use. It presents the test results, and you have links to the artifacts and logs and whatnot, and you have organized history. So it's mostly a developer tool, but it's completely independent of the workers and the policy entity. So it's replaceable and it's non-critical. And the whole infrastructure has some Juju charms, so that's basically Ubuntu's way of cloud deployment management. So it's very simple to deploy all of this into 3 local LXD containers. And with the exact same one command line, you can also deploy it into production on, say, OpenStack. And I can redeploy the entire infrastructure within minutes without losing any data. And yeah, the whole thing is maybe 200 or 300 lines of code, so which is about the same size as a single XML job for Jenkins, just say. So now we have all this. How did it change our life? It provides an effective carrot and sticks for developer. The carrot is, of course, as a developer, the better you make your tests, the harder it is for other people to break your software because of this reverse dependency triggering. For example, new kernels have a tendency to break LXC or AppArmor, or newer X libraries or servers have a tendency to break Qt, and in turn, newer versions of Qt tend to break KDE. And in Debian and Ubuntu, we have tons of KDE tests, so our Qt maintainer always has a hard time to land new Qt versions. And I guess they are swearing on this all the time. But as I said, once you actually get it to green, then you can land it with confidence. That's nice. The other effect is that these cross-package changes I mentioned, library transitions and so on, they either land completely or not at all. They will be forever stuck in proposed if you don't finish it all the way through. And this both ensures that you always have a good development series, and it also makes the release team's life much more easy. And of course, as a developer, you can whine all the time you want against the machine, but I have this deadline, I need to meet feature freeze and whatnot. machine is very patient and it won't give you anything, so you need to do your job properly. But of course, like there is no free lunch, it comes with a cost. As a developer, if you have a large amount of tests, then you need to keep the tests actually running. And for the most part, that's, of course, they can break with new upstream versions or changes to code. But sometimes they also break for entirely unrelated reasons. Like sometimes the cloud configuration changes, or an external website that you are talking to in your test changes or goes down, in which case it's probably an actual regression in your software, but still, I mean, people are chasing a lot of test regressions which are not entirely obvious at first. And of course, also having test infrastructure which is able to process tests at this scale is not entirely free. So we are basically building a reliable CI service on top of an naturally unreliable pool of hardware and cloud. So you need to invest a little bit on keeping that running. I mean, this fine gentleman over there took over the maintenance of that, and he can probably tell you a lot of the gory details of tracking down kernel loops and whatnot. And another big problem that we face in Ubuntu as a downstream is we import a lot of broken tests in Debian. As I said, we have so many tests now, and most of them come straight from Debian, but Debian doesn't gate yet, so eventually the failures land on us. For example, every new Ruby version that we import tends to break 2 or 3 modules, and in Ubuntu we just don't have the manpower or, quite honestly, the interest of tracking them down, so we just tend to ignore those. But by and large, after a few months of using this, people got used to it, and nobody really discusses the if anymore. I mean, people do see the value. And so the thing that we do discuss about is tweaking the policy and making tweaks to the infrastructure, or maybe discussing how to add a new architecture to it and so on. So in general, I think people feel a lot more safe that way. So, and that works really great for software which is native to Ubuntu, where we are the upstream. Say, Installer or Juju or Unity or whatnot, or Snappy. But as I said, it doesn't work so well when we are just a downstream. So of course these tests find bugs and keep them from landing in the development series all the time, but we then need to deal with them and file bugs upstream and work on patches and so on, and we're doing this. But it points out that running them in Ubuntu only is too late for most of the bits, because in Ubuntu, most of the code in Ubuntu just basically happens to us. It gets important. So what we really need to do is to push all of this upstream. So tests are already running in Debian. And we see here, Kwin failed sometime half a year ago, and nobody notices because nobody gets the output in Debian. But there's work underway to actually enable gating in Debian as well. And yeah, then this will be a lot nicer. But the real place where you want to hook this in is upstream. I'm heavily involved in the systemd community as a developer, both upstream and downstream. And back then, when we had a new upstream release of systemd, it took me like a week or 2 to figure out all the test regressions that it caused once I packaged the new upstream release. And it's a big pain point. So one of these days, I tweaked our package to be able to build an unmodified upstream source directly from a pull request without any patches, and then adjust the tests so that they would drop some Debian Ubuntu specific expectancies, and so that we are basically able to run our downstream systemd tests straight on an upstream source, and then integrated all of this with GitHub. I mean, GitHub is a wonderful webhooks interface which makes it quite easy to interface with, so that nowadays every pull request needs to pass exactly these tests. So this is an example of where things go wrong, and this is now developers' heaven. Because when this happens, the change is still fresh in the developer's mind. It won't land until it's all fixed. And as a result of that, every commit and by extension, every release of systemd is buildable everywhere. It passes the tests, and we have good releases finally. And so that enables things like daily PPAs. So basically, I have a script which takes common master, applies the Debian patches, runs the test, uploads it to the PPA if everything is great. And so it's fairly safe to use these daily builds because we know it's not going to break your computer. And basically, packaging a new upstream release now becomes an exercise in writing a good changelog, which is really the thing where you want to be at. And this is not really limited to systemd, so this is generic facility. We can interface with other projects on GitHub. Of course, it's always a capacity issue, and you need to negotiate the exchange of some credentials, but by and large, this is possible. Okay, well, thanks for your attention. So we still have a couple minutes left for questions. And if we don't manage to do it here, grab me in the hallway or write me an email or find me on our IC. I'm happy to talk about this stuff. I love it. Is the microphone working?
How do you handle if a package has to land together with another package? This means, for example, there's a new Qt version which has a new interface which provides to KDE, but there's also a new KDE version which provides to Qt.
Yeah.
And they have to land together.
Yeah, so the question was, how do you handle groups of packages which need to land together? Now, this is done by the proposed migration bits. So basically, if, for example, you upload a new GTK, which breaks the old Unity, and you then upload a new Unity, which depends on the new GTK, then this Britney script is able to figure out, like, GTK is uninstallable, Unity is uninstallable, but both together are installable, and both together, if I run the test of the new Unity against the test of the new GTK, then it's green, and then it lands them both as a group. So basically, if you do a library transition of Python 3.5 to 3.6, you will get like 1,000 uploads in the stage you proposed, and once you fix the last one, it all lands as a giant chunk. And this is the real point, so to get these cross-package updates done in an atomic and safe way. And this involves a lot of reasoning about dependency trees, and it's all a bit of black magic. I didn't write this, so this is the work of Debian mostly from Niels. And I'm very happy that we could just reuse this. So Debian does use that part also. So stuff that migrates from unstep to testing, and also only lands if library transitions are complete, and like packages built and installable, but it doesn't do the test.
So with the tests that actually get run, with the tests that actually get run by the Debian test control file, how do you personally feel about the distinction between tests that are testing the upstream code versus tests that are testing the code as it's packaged deployed in the system? So do you care whether the tests are run against the code as it's put into the package locations, or do you mind it's only run against the source tree?
I'm not sure whether I got it, but so the only thing all the package tests is the actual binaries that are in the archive. So we upload something to develop the post, and that gets a couple of DAGs, and they get installed into an actual system, and you only run those.
Yeah, so you test the actual installation of the binaries, yes. But when the test suite itself is run, it's often testing the source tree of the upstream code, not the actual installed version. They can be the same version, but it's actually not the same files.
Oh, you mean if you run like a make check kind of thing?
Yeah, because you're actually inside the developer environment at that point. Now, they should be the same thing. You haven't actually got the assurance that, because a lot of the test harnesses that we need to use can't actually test in /user/lib. They have to test in an unprivileged location. Right. So the question is, when you try to run upstream tests, which are designed to run against the build tree instead of the system, how do you do this? And this is indeed like one of the challenges. So if you have if you have your own thing like here, this will test the system install package. This is not against the source tree. But if you have packages upstream which are only run in the make check kind of style, you have to modify them to use the binaries installed in the system, because otherwise testing the build tree is not testing enough. You might have a perfectly well-running build tree, but then mess up the packaging. So, for example, you forget to actually install a file. So the tests need to run what's in the system. Depending on the test harness, that's simply not always possible.
Sure. I mean, for some upstream tests, it's easy to do. Like you introduce like a path variable or maybe a dash install test or something. Even Automake has a make install check interface, but not a lot of upstream software uses that. So if it's easy to change the upstream test suite to run against the system, then of course it's always preferable to use that. Sometimes it's hard, and I would say then just write a smoke test. So the point of that is not really to exercise all the little gory details of your API. That's what unit tests are for, and this is fine to run and make check. The point of that is to test integration and packaging, so that you can write your own, let's say, smoke tests, which only make sure that the package by and large works. Let's say for Apache, you install the package and you put like a var www index.html and you do a wget and make sure that you get back the file you expect. And this is actually, in this case, maybe an easier approach. But I hope that since more and more people are doing this, upstreams are more willing to take patches which make your test suite run against the install system as well. For example, GNOME has this for a while with the install test, and for example, the glib package actually has a binary which has glib install test, which you can just install and run, because they were doing the same thing in OS3, for example. So it becomes more popular. But it is a problem, yeah.
Yeah, and it's not the problem that you're currently trying to monitor or look at the actual test control script file and work out whether they're trying to do.
Yeah.
It's left to the maintainer to do that.
Yes, that's right.
So there is a potential problem there with the gating that you're using, because sometimes the gate is actually operating against not what you think it is. Whether that's taken into account or not.
And I might say, even if you actually just run the upstream test suite against your build tree, that's still better than doing nothing at all, because it still gives you the thing that if your dependency changes and then your build doesn't work anymore, because, for example, Q changes API, you have a kwin and it doesn't build anymore, it still points that out and it holds back the new queue until you fix kwin. So it's useful, it's just not, let's say, using the full extent of what it's supposed to do, but these REPL tests are definitely useful by themselves. And in fact, that's what KDE actually do. So they only basically run a check. And yeah, that's okay.
There's one question right here.
So lately, more and more programs are using multi-core, and the test suite are, in some cases, going to generate some intermittent issue. So how do you manage those? Intermittent issues, like in the test suite. So sometimes it's going to work, sometimes it won't. I know that it's ugly, but it's a reality for some software.
So these are always our favorites, of course, and this happens a lot. So, like everyone else, if it fails like 1 out of 10 cases, quite frankly, we push the retry button. And like in reality, the report that we have here, this actually has little recycle icons behind regressions, so a developer can just retry their own test. If it happens like 1 out of 10, it's okay-ish. If it happens more, then someone should actually sit down and debug it. And as I said, the point of this is it needs to be really easy to reproduce the tests locally. So basically with these auto package test command lines that I did, that I showed, these. There is tools which build VM images for you, standard VM images, which are basically almost the same than our cloud images. Or we have tools to build these standard containers, and there's existing tools to build your routes. And there's not really a lot of steps towards reproducing them yourself. And this has switches, for example, with dash shell. When the test fails, then you can SSH into the testbed and then debug your test and cycle faster. And yeah, this is basically the daily gory bit of what the developer needs to do to fix their test, because broken tests are useless. And anyone else?
Okay, there's
one
one
over there. Oh yeah.
Okay, I'll come there after this.
Can you tell a bit about the underlying compute hardware to support all this?
I'm sorry, I can't understand you. Huh?
Can you tell a bit about the underlying compute farm to do all this?
The compute farm? Oh, yeah.
The infrastructure?
Yeah. So we run all of this on, x86 and PowerPC we run on. Oh, okay. The question was, can I tell a little bit about the build farm that we use? So we have currently 3 OpenStack installations in Canonical, where basically whenever we have hardware, we toss it in there. And so we currently have, I think, 70 or so parallel workers for x86, so they can serve i386 and AIM64, and about 28 parallel workers for PowerPC. And as I said, for ARM and IBM Z series, we can't run them in VM sets, so we use LXC containers for those. And basically, you need to scale them to the degree where the maximum possible queue line is still parallel. So of course, this basically determines the delay that you're going to face when you try to land big updates like glibc. So and obviously, if you design it so that you can run glibc in half a day, then most of the time your infrastructure will just be there doing nothing. So this is the capacity issue. And as I said, we not just run distro tests, we also run tests for PPAs, and we also run tests for upstreams, and they all need to share the same thing. So this is indeed a bottleneck. For those, you can basically never have enough. So as a developer, you need to be a little patient sometimes. I mean, if you have a leaf package, it's fine. It can go through in like an hour. But for glibc, no, there is no fast updates of glibc. But I mean, in return, like the more tests you trigger, the more important your package is, and the more the gaining confidence aspect becomes. So, because if you upload glibc, it breaks 3 packages, which nobody looks at, you aren't going to discover this until you release. And so it's worth doing that. I'm not sure whether this was your question or you have more specific ones, but so the point is you run it on OpenStack so that maintaining the infrastructure is someone else's problem. I don't want to maintain the data center. This is IS's job, and they do this fantastically. And by and large, as a consumer, I do Nova boot and Nova delete, and I'm happy to get my VMs. And it just magically happens in the back.
Who had a question here?
Mm-hmm.
In your control file, you had isolate container, isolation container.
This one?
Yes, exactly. So what? How is it like a keyword, or you have to define another control file to define the container?
And no, these are fixed keywords. So these are defined capabilities in the AutoPackage test project. So all of these neat root, isolation container, and there's a couple of others, they have fixed meanings. I mean, sometimes we need new ones, yeah, so they basically say if you try to run this test in the root, it will just skip and say, sorry, your test bed doesn't have container isolation. And likewise, if you try to run the network manager test on LXC, it will say, sorry, it's not a full machine, so it gets skipped. So that's basically safe. And because if you do try to run it on your own machine, then it will do bad things. So yeah. So if you want a new one, then you need to talk to like the AutoPackage test guys like me, and then we need to define a new one. And it does happen.
Any other question here?
What?
There's one person.
Hello, do you have some infrastructure to handle complex applications and, for example, desktop applications?
There's no, sorry?
Do you have some infrastructure to handle tests of complex applications or desktop applications, which, for example, interact with user in some cases? For example, you can bump GTK for one minor version, and for example, in one minor version, they change the location of the character modules. Just change location in minor release. They are all bundled test path, which they supply with the application. But your system application just don't handle encoding correctly. Do you have some tests for desktop user applications?
Yeah, so I'm afraid I didn't get the whole question, but I think it was about how do we test desktop applications?
Yes.
Yeah, and we actually do. So originally you only had a cloud instance available, so there's a lot of stuff available. In particular, there's not Xorg installed by default. But the test can do whatever it wants to the VM. So we do have tests, for example, for the installer Unity, which basically install all the desktop bits and then configure the dummy Xorg driver. So then you can start LightVM, you can start Unity, and then maybe get the screen dump and make sure that it works. And we do have tests for testing GTK, or you can use Selenium for using browser tests and whatnot. So that actually works rather nicely. And we do this. But of course, it's limited to what you can do with like the dummy driver. So you can't rely on an actual graphics card there. So in order to do that, I mean, we do have use cases. We, for example, would like to run kernel tests or actual tests on an actual NVIDIA machine, actual ATI machine. And we did talk about this. And in principle, so we even have a plan how to implement this so that tests can declare, I need to run on actual hardware, but we didn't implement this yet. So this would require setting up real IM machines, like with Mars or in the rapid world satellite. So basically that you can automatically interact with real IM machines and then run tests there. We don't currently have that capability, but the structure would allow it.
So some tests will require manual guidance by human.
Sorry?
So some tests can be used in such infrastructure, but require some human interaction.
Yeah, so this is like anything which uses human interaction, like a test which uses human interaction, this is obviously not the target group here. I mean, this is not solving every kind of test case that you might have, but for the majority of bits, you should actually try to run your test suite so that it runs automatically. So there is, for example, Autopilot, which can test desktop applications in a non-interactive way because humans don't scale, right? But I mean, there will always be these kinds, and it's just out of scope, I'm afraid. Okay, well then, thank you, I guess. Yeah?